it's going to lose almost 2 MeV. So for this reason, it was important that we get the CR39 very close to the electrode that we think is producing this. And so this is the configuration we used, where we had the CR39 right behind, in this case, a screen, and in the solution. And so, you know, get the CR39 very close to the cell that we're experimenting with. And when we did that, in some cases, you know, you could actually see the layout of the screen. You can see some of that here. When you blew it up, you saw this sort of feature. Next. And then, but you know, this is other areas we would see this. Now this is in a magnetic field, and so many hits in the CR39 that was difficult to analyze. And in fact, one of the people that was working with us used to work in the hot fusion community, so he sent the CR39 to one of his friends who still worked in that community and said, hey, tell me what you think of this. And this guy was a purported expert in this, so in the analysis, and he sent back a note, and he said, gee, I see alphas that could be in this energy range, I see protons that could be in this energy range, I see, you know, went through a litany of things that he observed. And then he said, by the way, this is many more pits than what we see in our typical laser fusion experiments. What source irradiated this target? And my friend turned to me and he says, what do I tell him? If I tell him cold fusion, he's not going to talk to me again. And I said, tell him it's a Navy program that we're not prepared to talk about. So I think that, I suspect he knows by now, because kind of the lid is blown off of on the publicity side for the work that we're doing. But for several years, it was a Navy program. You know, the Navy has nuclear submarines, the Navy does all sorts of things. Hey, yeah, the Navy program we're not prepared to talk about yet. It makes a lot of sense. Next. Here's a case where we had a silver wire, and boy, you can sure tell where the wire was, you know, and in fact, so many pits that we actually would have to get out around the edges to analyze and look at the pits, and you see we get, you know, pits like this, and some of these things that look like 3-leaf clovers and 2-leaf clovers. I'll say more about those in a few minutes. But again, a lot of pits. We also saw, you know, some of this sort of thing, and we were challenged on the fact that CR39 is normally not used in a solution, and so therefore, how do you know this isn't chemical damage that caused this? And next, we did several things. You know, for example, we looked at and how do you know it's not background? You know, there's another. These are what our pits look like, and we developed a technique where if you focus on the surface of the CR39, you just see the rim, you know, but you don't really get a good image because it's, you know, a few microns down of what the tip looks like. So by using some false color, we would focus on the rim and then refocus down at the tip and use a different color. And by doing that, we would see these, and these in fact are very characteristic of high energy particles in CR39. Next. Another thing we did was we said, okay, let's just put the CR39 outside the cell. So we cut a hole in the cell, put a 6-micron Mylar window here, put the CR39 right next to it, and did the experiment. And when we did this, the tassel machine, the computer processing, found all of these pits. Now this is outside the solution. There's no way this could be chemical damage, and so, you know, this was another example. Now you have to realize, based on the LENR curves, that 6 microns of Mylar cuts off half, or 0.45 MeV proton, a 0.55 MeV tarton, 1.4 MeV helium-3, and 1.45 MeV alpha. So it subtracts a lot of energy just getting through the micron. Plus, then, you know, obviously there's a little bit of water here. So we were seeing some relatively high energy particles. Next. In addition to that, we did a whole bunch of other experiments to prove that this, in fact, was not chemical damage and not due to radioactive contamination of the cell. You know, this was one of the things people said, well, you know, it's just radioactive cosmic contamination, and I had fun with that one because I said, oh boy, you're telling me that this little wire here that I've got 1.5 volts on is focusing cosmic rays to cause this kind of yeah, how can, you know, wow, that is really Nobel Prize. So anyhow, you know, things like that, we had to deal with a lot of ridiculous comments, but even in this case, we even use things like copper chloride, which has, from an electrochemical standpoint, the same reaction as palladium chloride would have, deuterated water, and we didn't see the pits there. So, and this was reported in the European Physics Journal of Applied Physics in 2008. Okay, I mentioned that, you know, we were trying to figure out, okay, what is the energy level of the particles that we're seeing? And here's an example where we had 3 wires. We had the CR39 and we had 3 wires that we co-deposited onto at the same time. One being platinum, silver, and gold. And you see on the front, we saw this. On the back, we saw a lot more. In fact, you know, we didn't realize we had pits on the back until by accident we focused through CR39, saw all these pits, and realized, hey, wait a minute, something's going through that 10 micron CR39. So anyhow, or 1 millimeter CR39. So anyhow, we saw these pits, and you know, both for the platinum, in this case, we didn't see any from the silver on the back, and at the time, we weren't sure why that was. We still aren't positive, but we had an E field across here, and this would have been kind of in the middle of the E field, so maybe that was where the E field was the least, and it had the least impact. Next. Turning to the hot fusion community for the data that they had generated and how to analyze energies, particle energies using CR39. On the front, you typically get this kind of, you know, you get a lot of counts, a lot of pits that are in major axis and microns is this much, and then you get some more here like this. On the back, you see a shift where the count, the big ones, where the most are bigger, and so what these are up front, these are probably your alphas and so on, low energy. They go through the front. They don't make it all the way to the back. The back would be sort of like, you know, you shoot a bullet into something. It makes a small hole up front, but it may make a bigger hole as it comes out the back. And so in the back you see that. But now using the LET curves and the Mylar, you know, you can see that when we look at these on the back, it meant that we either had to have a 40 MeV alpha, a 10 MeV proton, or greater than 10, or a neutron, because a neutron will obviously go through the CR39 without and won't leave a track. On the other hand, if a neutron, and about 1 in 10,000 neutrons, will impact a carbon atom in a CR39, and if it has enough energy, it will shatter that carbon atom, and the carbon-12 becomes 3 alphas, and the alphas being ionized now leave a track that we can look for. Okay, next. So we compared our CR39 backside with some plutonium oxide source that we had, and you can see very similar, you know, circular shapes and so on. So everything, it again, from a consistency standpoint, stood up. Next. We then went to the books. Again, this comes out of the Phillips and others. Actually, Phillips was in the hot fusion community and wrote some of the seminal papers on the analysis of using CR39 to analyze high energy particles. He also worked at the Naval Research Lab. He's retired and is now at Georgetown, and he actually is one who worked with us and did a lot of analysis for us. So you know, we really had the experts in the field. But if you look at neutron billiards here, you know, if it recoils off something, it can go this way. It can knock something out that would come in and leave a pit, Case 2, if you got a heavier ion,